All right, so let's look at type 1 kinematic equation problems, or projectile motion problems. I'm sorry. So, in a type 1 problem, there's a few things we need to know when we're looking at it. So, we have a type 1 here. The first thing we need to know when we're looking at a type 1 problem is that we have level ground. So, our ground is level. Which means my change in displacement of y, or my displacement of y, is going to be 0 when it hits the ground. All right. Our max height occurs in these at 1/2 the range, which is our displacement of x, and 1/2 the time. Also in a type 1 problem, our initial speed is equal to our final speed. All right, so let's look at how to solve this in some problem-solving strategies. So a soccer player kicks a ball on a level playing field with an initial velocity of 11.3 meters per second at an angle of 35 degrees above the horizontal. Find the time of flight, the range, the maximum height, and the final velocity of the soccer ball. So our approach to solving these isn't going to change much. The very first thing we want to do is draw a picture or a diagram of what information the problem gives us. So it says a soccer player kicks a ball on a level playing field. So my playing field is level. So I know it's a type 1 problem because I have level ground. His initial velocity is 11.3 meters per second. So I know this velocity is 11.3 meters per second. And the initial angle is 35 degrees above the horizontal. And it wants us to find the time of flight, the range, the maximum height, and the final velocity of the soccer ball. All right. So our projectile would look something like this. Once he kicks the soccer ball, we know that it will go up, it will reach a maximum height, and then it will land. And we know this right here in the dead middle is 1/2 our range and 1/2 our time. And to make life a little bit easier, I'm going to say we're working in the positive range. But if we were to go south or back the direction we came from, it's going to be negative. So I've got my diagram drawn. Now I want to define directions, which I did. I drew my compass and I defined my directions. So now I'm going to label my variables. So I'm going to make myself a little T-chart, and I'm going to put horizontal on one side. And I think on y'all's papers, I already have this done for you. I'm going to put vertical on the other. And I'm going to list out all the horizontal and vertical variables. So my horizontal variables are my range, my velocity horizontally, and change in time. My vertical variables are my displacement on the y-axis, my initial y velocity, my final y velocity, acceleration, and change in time. All right, acceleration always pulls down. So I can go ahead and say my acceleration is negative 9.8 meters per second squared. And let's look at what else we can get out of this problem. We have an initial vertical velocity. And I said before that we can combine every vector into x and y components. So I'm going to divide this initial velocity, and I'm going to find my x velocity, and I can find my v1y from this initial v velocity. So I can say my initial velocity was 11.3 meters per second. So the cosine of 35 degrees, or that's my angle, so I'm going to use SOHCAHTOA here. So my cosine of an angle is equal to adjacent. I don't know that, but that's going to be my initial or my x velocity, my horizontal velocity, over my hypotenuse, which is 11.3 meters per second. When I solve this, my horizontal velocity is going to be 9.26 meters per second. So I can plug that in right here. I have 9.26 meters per second. That's what that horizontal velocity is. All right. These trig ratios also tell me that my sine of my angle is equal to my opposite. I don't know what that is. That's what I'm trying to find out. V1y over my hypotenuse, which is 11.3 meters per second. So I can solve that out. And my initial vertical velocity is 6.48 meters per second. So I can plug that into my known column. That's one more thing I know. All right. Last but not least, we're on level ground. So when the ball hits the ground, we're at 0 meters for our vertical change here. It starts and ends at the exact same height. So our displacement on the y-axis is 0 meters. And the way to solve these problems, there's 3 types, and the way to solve them eventually is going to become logarithmic to you. We're going to follow the same procedures once we identify the type over and over and over again. So I've labeled my variables. I've used my trig relations to figure out my horizontal velocity and my initial vertical velocity. The first thing I'm going to solve for, I guess step 4 could be solve. This could be 4A. We're going to solve for time of flight. So we're going to go back to our kinematic equation, and we're going to find a kinematic equation that has acceleration, change in displacement y, initial velocity of y, or initial velocity, and change in time, because this is what we're looking for. And we're going to get this kinematic equation. Our change in our displacement is equal to our initial velocity, change in time, plus 1/2 acceleration, change in time, squared. So let's take this equation and apply it to what we're doing. So I'll put 4a over here so you know what I'm working. First thing I'm going to do is write down my equation. So I have my displacement, and I'm going to use y here. I have my initial velocity of the y-axis, change in time, plus 1/2 acceleration, change in time squared. My change in displacement on the y is 0. My initial velocity is 6.48 meters per second. I am looking for a change in time. Plus 1/2 times my acceleration, negative 9.8 meters per second squared, change in time squared. I'm going to distribute my 1/2, so I'm going to get 0 meters is equal to, and I'm going to drop these units just to make it easier for you to see, 6.48 change in time minus 4.9 change in time squared. I'm going to factor out a change in time. And I'm going to set each of my factors equal to 0. So change in time is equal to 0. That is going to be my start time. It started at 0. Then I have 6.48 minus 4.9 change in time is equal to 0. So I have negative 6.48 equals, I flipped that, sorry, negative 4.9 change in time. So my change in time is going to be equal to 1.32 seconds. So that's going to be my time when the ball hits the ground. So I can go back up and I can fill this in now. I know my time when the ball hits the ground is 1.32 seconds. And I can write that on both times because remember, time applies to horizontal and vertical. All right, after I solve for the time of the flight, I'm going to solve for range. So range is our horizontal displacement. To solve for range, you're going to say velocity is equal to a change in displacement over a change in time. So I'm going to come down here and apply that to this. So I'm going to say that my velocity on my x-axis is equal to my total displacement on my x-axis over the change in time. My velocity on the x-axis was 9.26 meters per second. I'm looking for my range. I don't know that. And I know my change in time now is 1.32 seconds. So when I solve, I'm going to get that my range is equal to 12.25 meters. So that's how far this soccer ball went. From start to finish, it went 12.25 meters. So I can plug that number in up here too now. I know that. All right. The next step is to find max height. So 4C is max height. And I'm going to use this same kinematic equation. So I'm just going to draw an arrow in there because I'm going to use the same kinematic equation to solve for my maximum height. And I need a new sheet of paper because I am out of room on mine. You have probably gone to the next sheet, and that is completely fine. All right, so at our maximum height, which is right here, our time is half. It's half of our time and half of our total range. Well, range isn't in this kinematic equation, so I'm not going to need that. But I am going to need to half my time. So my change in time at max height is equal to my total time, 1.32 seconds, divided by 2. So at our max height, our time is 0.66 seconds. All right, so at 0.66 seconds, where is the ball in the air? That's what we're looking for. And I said we were going to use this kinematic equation we used before. So our change in displacement, or our displacement on the y-axis, is equal to initial velocity, change in time, plus 1/2 acceleration, change in time squared. This is what we're looking for. So our maximum height, our initial velocity y was 6.48 meters per second. Our change in time, so we're looking for our height when the change in time is 0.66 seconds plus 1/2 times negative 9.8 meters per second squared times our change in time again, 0.66 seconds squared. Our math is going to come out to, at 0.66 seconds, our height is 2.14 meters. And there's nowhere to write this on these variables. So this is just kind of a piece of nugget of information we have to hold on to for when we write our answer out. The last thing we're going to solve for with this is going to be, for D, our final step, our final velocity. All right, here we go. I'm going to flip this over so I have some clean area to work with. So we know some things we can plug in that we know about our final velocity. Our velocity on the x-axis is constant, right? So we need to find our final velocity on the y-axis. So the kinematic equation I'm going to go to is going to be my velocity, my final velocity is equal to my initial velocity squared on both of those plus 2 acceleration change in displacement. So I'm going to write this over here just so I know which equation to remember to use. And I'm going to plug in what I know. I'm looking for this final y velocity. I don't know what that is. So that's what I'm going to leave right here. Squared is equal to my initial velocity, y, was 6.48 meters per second, squared, plus 2 times my acceleration, negative 9.8 meters per second squared, times my final change in displacement y. So my final change in displacement y was 0. So all of that will be 0. I'll take the square root of both sides, and I will get my final velocity of y is equal to plus or minus 6.48 meters per second. So I need to draw what's going on here at the very end. So at the very end, we have hit the ground. And once we've hit the ground, our velocity isn't 0. There's still velocity here. And I just said that my final y velocity was 6.48 meters per second. My x never changes. So my velocity at x is equal to what it's been. My horizontal velocity is never going to change. So it's going to be 9.26 meters per second. So I need to solve for what this is. This would be my final velocity. So I can say a squared 6.48 meters per second squared plus 9.26 meters per second squared equals my velocity final squared. So my final velocity is equal to 11.3 meters per second. And let's compare these two triangles really quick. My initial velocity was 11.3 meters per second. My final velocity was 11.3 meters per second. My initial horizontal velocity was 9.26. My final horizontal velocity was 9.26. My initial y velocity was 6.48 meters per second. My final y velocity was 6.48 meters per second. So in a type 1 parabola or a type 1 projectile, they will be the same, which means instead of solving for this angle, I can just say that this angle is 35. I could do the math, but my numbers here are exactly the same as my numbers here, so I'm going to get that same angle. If you wanted to do the math, you would use your trig ratios to solve that. So you'd go back to SOHCAHTOA. Last but not least, I have to write my answer. So the soccer player kicked the ball on a level playing field with an initial velocity of 11.3 meters per second at an angle of 35 degrees above the horizontal. The ball's time of flight is 1.3 seconds with a range of 12 meters, a maximum height of 2.14 meters, and a final velocity of 11.3 meters per second, 35 degrees. I'm going to put BTH. That just means below the horizontal. So anytime you need to solve one of these or solve a projectile motion problem and you realize that it's a type 1, you're going to follow these steps over here. So you're going to draw a diagram. You're going to define your directions, label your variables, use SOHCAHTOA to find the x and y components, and then apply that to solve for your change in time, your range or your total change in displacement of x, your maximum height, and your final velocity. And this is the order you'll use. I promise it seems confusing at first, but the more you work, the more logarithmic and the more routine it will get. And it almost becomes comforting after a while to solve these.